When people talk about early spaceflight, they often talk about breakthroughs, new engines, new materials, new computers, a steady march toward better technology. But that framing misses what actually defined the era. Early spaceflight was not driven by the pursuit of the best possible solution. It was driven by a series of choices about what could not exist at the same time. Every major decision forced something else off the table. Speed came at the expense of certainty. Capability came at the expense of understanding. Redundancy came at the expense of clarity. Flexibility came at the expense of stability. These were not temporary shortcomings waiting to be resolved. They were structural trade-offs baked into the systems from the beginning. The popular story suggests that engineers were always trying to maximize performance, safety, and reliability all at once, limited only by technology. In reality, the constraints were not just technical, they were temporal, organizational, and cognitive. Spacecraft had to be designed not only to function, but to be understood, tested, trained on, and operated by real people under pressure. That requirement narrowed the design space dramatically. A spacecraft could be lighter, or it could be stronger. It could be more capable, or it could be simpler to operate. It could incorporate every improvement discovered during development, or it could remain stable long enough for crews and controllers to learn how it actually behaved. Very often, it could not do both. These trade-offs were not the result of poor planning. They were the unavoidable outcome of trying to do something unprecedented under fixed timelines, limited budgets, and incomplete knowledge. Spaceflight did not begin in a world where optimization was possible. It began in a world where choices had consequences that could not be undone. Once a path was chosen, other paths closed. Once hardware entered production, design freedom narrowed. Once training began, system behavior had to remain consistent. Once missions were scheduled, uncertainty had to be absorbed rather than eliminated. Early space programs learned this quickly. They learned that adding capability late often made systems harder to manage, not safer. That increasing redundancy could introduce ambiguity instead of protection. That improving performance in one area frequently degraded margins somewhere else. That a system optimized for peak performance could become fragile when operated outside ideal conditions. They also learned something less intuitive. That safety did not always come from building the best possible machine. It often came from building a machine that everyone understood deeply, even if that machine carried limitations. This required choosing what not to fix, choosing what not to add, choosing what not to optimize. These decisions shaped everything that followed. They influenced spacecraft architecture, mission design, training philosophy, and operational discipline. They shaped how authority was distributed, how risk was discussed, and how failure was anticipated. Early spaceflight was defined less by what engineers achieved than by what they deliberately gave up. This episode is about those choices, not as compromises, not as failures of imagination, but as the trade-offs that made spaceflight possible at all. Before there were routines, before there was confidence, before success could be repeated, there were decisions that narrowed the field of options and locked entire programs into particular ways of working. Understanding those trade-offs is the only way to understand how early spaceflight actually worked. Part 1. Trade-offs are not compromises. In everyday language, a trade-off is often treated as a failure. It suggests that something better was possible but not achieved. That an ideal outcome existed, and circumstances forced a lesser one instead. When people talk about trade-offs this way, they usually imagine a temporary shortfall, something to be corrected later, once conditions improve. That is not how trade-offs functioned in early spaceflight. A compromise implies that two desirable outcomes could, in theory, coexist. A trade-off exists when they cannot, when choosing one permanently excludes the other. Early spaceflight was defined by these kinds of choices. A spacecraft could be light enough to reach orbit or robust enough to absorb large margins. It could be highly capable or understandable under pressure. It could be modified continuously as knowledge improved, or it could remain stable long enough for people to learn how it actually behaved. These were not matters of preference. They were matters of physics, time, and human limitation. Once a choice was made, it reshaped everything downstream. Design decisions locked in mass and structure. Mass and structure locked in propulsion requirements. Propulsion requirements locked in testing regimes and operational profiles. Operational profiles shaped training, procedures, and mission rules. At each step, options narrowed. This is why trade-offs in spaceflight were not isolated decisions. They were cumulative. Each one constrained the next, creating a system that could only exist in a particular form. The popular image of engineering suggests that trade-offs are negotiated continuously, with the goal of eventually resolving them through better design. Early spaceflight did not work that way. Many trade-offs were settled early, not because they were ideal, but because changing them later would have fractured the system. Once hardware entered production, the cost of change rose sharply. Once crews began training, consistency became more valuable than improvement. Once missions were scheduled, uncertainty had to be managed rather than eliminated. This forced a shift in how success was defined. Instead of asking whether a design was optimal, engineers and program managers asked whether it was coherent, whether the system, as a whole, could be built, tested, understood, and operated without breaking under its own complexity. Coherence became a form of safety. A system that was internally consistent, even if imperfect, allowed people to build reliable expectations. Those expectations supported training, decision-making, and coordination under stress. A system that changed frequently, even in pursuit of improvement, disrupted that process. This is why early spaceflight often appears conservative in hindsight. Designs look underpowered. Interfaces look awkward. Capabilities look limited compared to what might have been possible with more time or different priorities. But those limitations were often the result of choosing stability over expansion. Not because engineers lacked imagination, but because they understood how fragile complex systems become when too many dimensions are allowed to vary at once. Trade-offs were also shaped by who had to live with their consequences. Engineers might propose improvements. Program managers might evaluate schedule impact. But crews and controllers were the ones who had to operate the system in real time, with incomplete information and limited ability to recover from mistakes. A design that looked acceptable on paper could become dangerous if it increased workload, ambiguity, or cognitive burden during critical phases. A system that demanded constant interpretation was harder to manage than one that behaved consistently, even if that behavior included limitations. This is why early spaceflight placed such a premium on understandability. Not simplicity in the abstract, but learnability. The ability for people to develop intuition about how the system behaved across a range of conditions. That intuition could not form if the system changed too often or behaved differently after every modification. Trade-offs in this context were decisions about where understanding would live. Would it live in hardware, through redundancy and automation? Would it live in procedures, through strict rules and sequencing? Would it live in people, through training, experience, and judgment? Most often, it lived in some combination of all three. But it could not be maximized everywhere at once. Choosing to add capability in hardware often reduced reliance on human judgment, but increased system complexity. Choosing to limit capability preserved clarity, but placed greater demands on operations. Choosing to automate reduced workload in some areas, but introduced new failure modes that were harder to diagnose. Each choice closed doors. And once closed, those doors rarely reopened. This is why early spaceflight cannot be understood as a gradual march toward better solutions. It was a narrowing process, a continuous winnowing of possibilities until only a small set of workable options remained. The trade-offs that defined early spaceflight were not mistakes waiting to be corrected. They were the conditions under which flight was possible at all. Understanding that reframes everything that follows. Because once trade-offs are understood as structural rather than temporary, the next question becomes unavoidable. If spaceflight required giving something up at every step, what exactly did programs choose to sacrifice first? Part 2. Speed was chosen over certainty. One trade-off overshadowed nearly every other decision in early spaceflight. Time, not as an abstract pressure, but as a fixed condition that shaped what kinds of systems could exist at all. Early space programs did not operate in an environment where certainty could be accumulated slowly. There was no long runway for sequential development, where designs could be finalized, tested exhaustively, and then flown. Schedules were set before systems were understood. Deadlines arrived before confidence did. That did not mean engineers ignored uncertainty. It meant they had to decide how to live with it. The traditional engineering model assumes a sequence. Design first, test next, operate last. Knowledge accumulates before exposure to risk. In early spaceflight, that sequence collapsed. Design, testing, training, and operations overlapped by necessity. Spacecraft were being built while missions were still being planned. Procedures were written while systems were still changing. Crews trained for vehicles whose final configurations were not yet settled. This was not recklessness. It was the only way forward. Waiting for certainty would have meant missing launch windows, losing political support, and fracturing programs before they could prove viability. Time itself became a constraint that could not be negotiated. As a result, early spaceflight adopted a different posture toward knowledge. Instead of attempting to eliminate uncertainty before flight, programs learned to absorb it gradually. They accepted that some understanding would only emerge through operation. Learning moved into motion. This required a deliberate shift in priorities. Systems were designed to be flyable rather than complete. Architectures were chosen for executability rather than elegance. Decisions favored paths that could be carried forward consistently, even if better alternatives existed on paper. Once those paths were chosen, flexibility narrowed rapidly. A design that remained fluid for too long became impossible to integrate. A system that changed continuously became impossible to train against. A spacecraft that evolved faster than people could adapt became unsafe, regardless of its technical merits. This is why early space programs locked designs earlier than engineers would have preferred. Stability became more valuable than improvement. A system that was imperfect but fixed allowed organizations to build understanding. A system that was continuously improved prevented that understanding from converging. The trade-off was explicit: sacrifice potential performance gains in exchange for coherence. That choice shaped how risk was handled. Uncertainty did not disappear when designs were frozen. It moved. It shifted from hardware into operations, training, and decision-making. Instead of asking whether a system could fail, teams focused on how failure would unfold and whether there was time to respond. Speed forced prioritization. Some questions were answered rigorously. Others were deferred. Some risks were eliminated. Others were carried forward intentionally. This was not because engineers underestimated the dangers. It was because they understood that delaying decisions created different dangers, ones that were harder to see and harder to manage. In a compressed timeline, indecision is not neutral. Every unresolved question consumes attention. Every late change demands revalidation. Every additional test pushes something else off the schedule. As programs matured, the cost of change rose faster than the benefits of additional certainty. At a certain point, certainty itself became destabilizing. More data introduced more disagreement. More analysis revealed more edge cases. More optimization exposed more interactions that could not be fully resolved before flight. The goal shifted again. Instead of asking, "Do we know enough?" programs began asking, "Do we know enough to proceed?" That distinction matters. Knowing enough to proceed does not mean being confident in every subsystem. It means understanding where uncertainty lives, how it manifests, and what it will demand from the organization when it surfaces. Speed forced programs to make that judgment earlier than was comfortable. It also forced them to accept that some knowledge would arrive late. Telemetry anomalies would appear only in flight. Thermal behavior would diverge subtly from predictions. Human interaction with systems would reveal strengths and weaknesses no simulation could capture. Early spaceflight accepted this as a condition, not a failure. Learning did not stop at launch. It continued through each mission, with each flight validating part of the system while carrying other uncertainties forward. Programs advanced not by resolving everything at once, but by surviving long enough to learn incrementally. This approach was fragile. It required discipline. It required restraint. It required resisting the urge to fix everything that looked imperfect. Speed demanded that programs decide which uncertainties could be lived with, and which ones could not. Those decisions were rarely obvious. They involved judgment, experience, and an understanding of how tightly coupled this system had become. Choosing speed over certainty did not mean ignoring risk. It meant accepting that certainty would arrive unevenly and that the system had to remain stable long enough for people to build trust in how it behaved. This is why early spaceflight often appears to have moved forward despite unresolved questions. In reality, it moved forward because of them. The inability to wait forced programs to confront trade-offs earlier, lock decisions sooner, and commit to systems that were good enough to be understood. Speed was not an accelerant applied to a finished design. It was a constraint that reshaped what kinds of designs were possible in the first place. And once speed had claimed its priority, it imposed another consequence. If time limited how much could be known, then capability itself had to be constrained to preserve understanding. That is the next trade-off. Part 3. Capability was limited to preserve understanding. As early space programs moved forward under compressed timelines, another trade-off became unavoidable. Not everything that could be built should be built. This was not a rejection of capability, it was a recognition of human limits. Spacecraft were not operated by abstract operators with infinite attention and perfect recall. They were flown by crews and supported by controllers who had to interpret data, recognize patterns, and make decisions under pressure. A system that could do more than people could reliably understand was not safer. It was fragile. Capability increases complexity. Each new mode, feature, or automated behavior adds interactions that must be anticipated, trained for, and recognized in real time. Those interactions multiply faster than intuition can keep up. Early spaceflight encountered this quickly. Adding performance often meant adding states the system could enter. Adding automation meant adding transitions that were difficult to observe directly. Adding flexibility meant adding decision points that had to be navigated correctly under time pressure. None of these were free. A spacecraft with more capability required more training. More training required more stable behavior. More stable behavior required fewer late changes. At a certain point, capability began to work against understanding. Engineers recognized this, even when it ran counter to instinct. The temptation to add features was strong. Each improvement promised to reduce workload, increase safety margins, or expand mission options. But each improvement also demanded that the organization relearn how the system behaved as a whole. Late in development, that relearning became dangerous. A system that crews had trained against for years carried a shared mental model. Controllers knew which readings fluctuated and which ones mattered. Crews developed a feel for timing, response, and delay. Procedures were written with specific behaviors in mind. Adding capability late disrupted that model. Even small changes altered how systems interacted. Automated responses could mask underlying conditions. Additional modes created ambiguity about what state the system was actually in. Increased flexibility made it harder to anticipate what the system would do next. Understanding eroded quietly. This is why some capabilities were deliberately left out. Not because they were impossible to build, but because they would have required too much relearning, too late. A capability that could not be fully integrated into training, procedures, and operational intuition was a liability, not an asset. Limiting capability was a way of protecting coherence. A system that did fewer things, but did them consistently, allowed people to build reliable expectations. Those expectations were critical when something deviated from plan. Recognition was faster than analysis. Familiarity reduced cognitive load at exactly the moments when attention was scarce. This did not mean early spacecraft were simple. They were complex in tightly controlled ways. Complexity was concentrated where it could be managed and avoided where it could not. Systems were designed to behave predictably, even if that meant accepting inefficiency or manual intervention in some cases. Automation illustrates this trade-off clearly. Automation can reduce workload, but it also obscures causality. When a system acts on its own, understanding shifts from direct observation to inference. If automation behaves unexpectedly, diagnosing the problem becomes harder, not easier. Early spaceflight therefore used automation selectively. Tasks that were repetitive and well characterized were automated. Tasks that required judgment or adaptation remained human-centered. This balance was not philosophical, it was practical. Automation that could not be verified across all relevant conditions was treated as a risk. Limiting automation preserved transparency. When something went wrong, crews and controllers needed to understand why. A system that hid its internal state behind layers of automation could fail in ways that were difficult to interpret quickly. Capability was also limited to protect communication. Spacecraft operations depend on shared understanding across teams. Controllers must communicate clearly with each other and with crews. Procedures must be interpreted the same way by everyone involved. Introducing too many options increased the chance of misalignment. When systems were constrained, language stayed precise. Expectations stayed aligned. Decisions could be made quickly because everyone understood the boundaries. This is why early spaceflight often favored fewer modes, fewer options, and fewer degrees of freedom than later designs might have allowed. It was not a lack of ambition. It was an investment in comprehension. The goal was not to build the most capable machine imaginable. It was to build a machine that people could understand deeply enough to trust under stress. Capability was not rejected, it was rationed. And that rationing was one of the defining trade-offs of early spaceflight. But limiting capability introduced another tension. If systems were deliberately constrained, then safety could no longer rely solely on hardware. It had to emerge from how systems were used, monitored, and backed up. That brings us to the next trade-off. When redundancy was added to compensate for limitations, it did not always make systems safer. Sometimes it made them harder to manage. Part 4. Redundancy, complexity, and the illusion of safety. Redundancy is often treated as an unambiguous good. If one system can fail, add another. If one component is fragile, back it up. If something matters, duplicate it. In simple systems, this logic works well. In tightly coupled systems like spacecraft, it becomes more complicated. Redundancy does not just add protection, it adds structure. It introduces new components, new interfaces, new behaviors, and new decisions about which signals to trust when systems disagree. Each additional layer changes how the system must be understood and operated. Early spaceflight encountered this tension repeatedly. Adding backup systems increased mass, power consumption, and thermal load. It required additional wiring, sensors, and logic to determine which system was active and when. It introduced failure modes, where the redundancy itself became the source of ambiguity. When two systems disagree, someone has to decide which one is right. That decision is not automatic. It requires interpretation, context, and time. Under pressure, ambiguity can be more dangerous than a clean failure. A single failed system produces a clear signal. A disagreement between systems produces uncertainty. Early space programs learned that redundancy could shift risk rather than remove it. Multiple systems increased the number of possible stakes a spacecraft could enter. They expanded the space of failure combinations. They demanded more from training, procedures, and real-time judgment. Redundancy also complicated diagnosis. When a system behaved unexpectedly, determining whether the problem lay in the primary system, the backup, or the logic connecting them took time. That time was not always available. In some cases, switching to a backup too quickly could make the situation worse, not better. This is why redundancy was applied selectively. Not every system was duplicated. Not every failure was protected against in the same way. Engineers evaluated redundancy not only by what it guarded against, but by what it introduced. A backup that failed differently from the primary system could be valuable. A backup that behaved almost the same way could create false confidence. A backup that required complex switching logic could become a liability under stress. Redundancy also interacted with human behavior. When operators know a backup exists, they may tolerate risk differently. Margins can be consumed more readily. Systems may be pushed closer to their limits under the assumption that protection is available. Over time, this can erode the very safety redundancy was meant to provide. This phenomenon is subtle. It does not require recklessness. It emerges from routine success. When backups work repeatedly, they fade into the background. Attention shifts elsewhere. The system is trusted to catch errors automatically until it does not. In early spaceflight, engineers and operators were aware of this risk. They understood that redundancy could create complacency if not accompanied by discipline. Backup systems were treated as last resorts, not conveniences. Procedures emphasized restraint. Switching to redundancy was often delayed deliberately to preserve understanding of what was actually failing. Redundancy also affected communication. When multiple systems were available, teams had to agree on when and how to use them. Ambiguity about authority or criteria could lead to hesitation or conflicting actions. Clarity mattered more than coverage. In some cases, it was safer to accept the risk of a single system than to introduce confusion about which system should be trusted. This runs counter to intuition. From the outside, more systems look safer. From the inside, more systems demand more coordination, more interpretation, and more judgment. Safety depends not only on what exists, but on how clearly its behavior can be understood under pressure. Early spaceflight did not reject redundancy. It treated it with caution. Redundancy was added where failure modes were well understood, switching was straightforward, and the operational implications could be trained for realistically. It was avoided where it created ambiguity that could not be resolved quickly. This meant that some systems flew with less backup than might seem comfortable in hindsight, not because engineers underestimated the risk, but because they understood how complexity itself could become hazardous. Redundancy was not a universal solution. It was a trade-off. Adding protection in one dimension often increased vulnerability in another. The challenge was not to maximize redundancy, but to place it where it improved clarity rather than obscured it. This is why redundancy did not always mean safety. Sometimes the safer system was the one that failed clearly, predictably, and in ways that people knew how to respond to. That realization pushed early space programs toward a different understanding of safety. Safety was not just about preventing failure. It was about preserving the ability to understand what was happening when something went wrong. And that understanding depended as much on organizational behavior as on hardware design. That leads to the next trade-off. If machines could not be made perfectly safe through redundancy alone, then success depended on how responsibility, authority, and judgment were distributed across the organization. Part 5. The organizational reality behind mission success. By the time early space programs reached operational maturity, it was clear that safety could not be engineered into hardware alone. The machines mattered. The designs mattered. But the outcomes depended just as heavily on how responsibility, authority, and judgment were organized around those machines. Spaceflight was not carried out by isolated experts making independent decisions. It was executed by tightly coordinated teams operating under time pressure, uncertainty, and incomplete information. How those teams were structured shaped what kinds of decisions were possible in the moment. This introduced another trade-off. Decisions could be centralized to preserve consistency or distributed to preserve speed. Authority could be held at the top to reduce risk or pushed outward to those closest to the data. Each choice came with consequences. Early space programs experimented with these boundaries. Some decisions were deliberately centralized. Mission rules defined what could and could not be done without higher approval. Certain system states triggered mandatory consultation. These constraints were not about control for its own sake. They were about preventing individual judgment from fragmenting the system. Other decisions were pushed outward. When time mattered, authority had to sit close to the problem. Crews were trusted to respond to rapidly evolving conditions. Controllers were empowered to act within defined boundaries. Waiting for consensus in every situation would have introduced delay that the system could not tolerate. This balance was not static. It shifted depending on mission phase, system behavior, and confidence in understanding. As teams learned how the spacecraft behaved, authority could be delegated more confidently. Where behavior remained uncertain, decision-making remained centralized. Organizational structure became a safety mechanism. Clear lines of responsibility reduced ambiguity. Defined roles ensured that someone was accountable for interpreting data, making calls, and communicating decisions. Redundancy in people, like redundancy in hardware, had to be managed carefully to avoid confusion. Too many voices slowed response. Too few increased blind spots. Early spaceflight learned to value coherence over inclusivity in critical moments. This did not mean suppressing dissent. It meant channeling it productively. Disagreement was encouraged during planning, review, and simulation. Once a mission was underway, alignment mattered more than debate. Procedures reflected this reality. Checklists were not just technical tools. They were coordination devices. They ensured that everyone shared the same mental model of what was happening and what would happen next. Mission rules clarified decision thresholds so that action did not depend on ad hoc negotiation under stress. Training reinforced organizational discipline. Simulations were designed to stress not only hardware, but communication. Teams practiced working through ambiguous situations where information was incomplete or misleading. The goal was not to eliminate disagreement, but to resolve it efficiently without fragmenting action. Over time, teams developed trust. Not blind trust, but calibrated trust. Controllers trusted crews to operate within constraints. Crews trusted controllers to interpret data accurately and provide guidance. Managers trusted teams to escalate issues appropriately. That trust was built through repetition and shared experience. It could not be rushed. This is why organizational stability mattered as much as technical stability. Frequent changes in structure, leadership, or roles disrupted trust. Teams had to relearn not only the system, but each other. In high-risk environments, that relearning carried its own dangers. Early space programs learned to protect continuity. Roles remained consistent. Interfaces between teams were kept stable. Authority was exercised predictably. These choices reduced flexibility, but they increased reliability. Success depended on this reliability. When something went wrong, teams needed to respond as a unit. Fragmented authority or unclear responsibility would have slowed action and increased risk. The organization had to function as a single system, not a collection of experts. This is often invisible in retrospect. The focus tends to fall on hardware, on dramatic moments, on individual decisions. But those moments were shaped by organizational choices made long before flight. Choices about who decided what, when, and under which conditions. Early spaceflight succeeded not because organizations were flawless. They were not. It succeeded because organizations were structured to manage imperfection. Authority, communication, and responsibility were aligned with the realities of the system they supported. That alignment did not eliminate risk. It made risk manageable. And it revealed a final, quieter truth. The success of early spaceflight depended less on preventing failure than on ensuring that when failure occurred, the organization could still think clearly, act coherently, and adapt without breaking. That understanding brings us to the final question of the episode. What did all of these trade-offs ultimately produce? Not in hardware, not in procedures, but in how safety itself came to be understood. Part 6. What early spaceflight gave up so it could exist. When early spaceflight is remembered, it is usually remembered for what it achieved: orbit, rendezvous, landing, return. What is less visible is what had to be given up so those achievements could occur at all. Early space programs did not move forward by accumulating advantages. They moved forward by narrowing possibilities. At each stage, something had to be sacrificed to preserve coherence. Flexibility was given up so systems could stabilize. Optimization was given up so understanding could deepen. Elegance was given up so behavior could remain predictable. Margin was given up so schedules could hold. None of these were accidental losses. They were deliberate choices made in recognition of how complex systems actually behave when pushed beyond what is comfortable. Spacecraft were not built to be the best possible machines under all conditions. They were built to be survivable within specific ones. That required limiting what systems could do, how often they could change, and how much variation the organization had to absorb at once. Safety emerged, not from eliminating every weakness, but from aligning expectations with reality. When teams understood exactly what had been given up, they knew where caution was required. When boundaries were clear, behavior adjusted naturally. When limitations were acknowledged openly, they became part of the system's operating logic rather than hidden hazards waiting to surface. This understanding reshaped how success was measured. Success was not defined by peak performance. It was defined by repeatability, by the ability to operate again and again without fracturing under pressure. Early spaceflight achieved this by resisting the temptation to chase perfection. Instead, it focused on building systems that people could learn deeply, trust under stress, and adapt around when conditions deviated from plan. The trade-offs that made this possible were not signs of failure, they were signs of maturity. This perspective also reframes how risk should be understood. Risk was not something to be eliminated before flight. It was something to be distributed intelligently across hardware, procedures, training, and organizational structure. Each trade-off relocated risk rather than removing it. What mattered was whether the system could still function coherently when that risk became real. That coherence was fragile. It depended on stable designs, disciplined operations, clear authority, and shared understanding. When any of those eroded, safety eroded with them. The lesson of early spaceflight is not that trade-offs are unfortunate necessities. It is that trade-offs are the mechanism by which complex systems remain viable at all. Every system built under constraint will carry imperfections forward. What determines whether those imperfections become manageable conditions or catastrophic surprises is how honestly they are acknowledged and how deliberately they are integrated into daily operation. Early spaceflight chose the harder path. It chose to live inside its trade-offs rather than deny them, to accept limits rather than obscure them, to preserve understanding even when improvement was possible. That choice did not make spaceflight easy, it made it possible. In the next episode, we will look more closely at how risk itself was managed when failure was not hypothetical but expected, and what it took for organizations to continue operating when success could not be guaranteed. Subscribe to continue exploring how space programs actually worked and how complex systems survive when ideal options are not available. Each episode examines one constraint and the structures built to live inside it.